do not consider the 3D FEM is your magnetics calculator. It's not. The main reason is because primarily 3D FEM relies on physics and numerics. So it doesn't know about AL value of your core because AL value is usually given for a specific core type. FEM will not operate with LA values. The same way, you cannot push it to apply some specific magnetic flux value in the core. So let's say you have a core and you would like to say that, okay, I have 0.5 Teslas in the core. Okay, fine. But consider that in 3D FEM, because it operates on physical, in physical paradigm, we have to be sure that the divergence of magnetic flux is 0. And the same with currents. So how are you going to apply this magnetic flux to be sure that the divergence is 0? It's very complicated to set it up analytically. So usually we will not set up those physical values, but instead we will excite our windings with excitations, with voltages and currents. And then the software based on numerics and physics will do the rest for us. Also, when you're doing FEM simulations, you have to keep in mind that mesh quality and material data that you have is paramount. So if you put garbage in, you will get garbage out. And FEM tool that you're using will not be responsible for that. So when you are doing simulations, you are responsible for the end result as much as the tools that you are using. And it's also your kind of responsibility to be sure that you stay within the limits of the numerical methods that you're using. However, from our side, from software developer side, it's our responsibility to teach you, to provide all the details to inform you. Also, do not think that you will efficiently able to solve all the problems that you have. There could be cases that are not worth trying, like just skip it, take another case and solve it with FEM, especially 3D FEM. It will be quite time consuming, although in some cases you can easily get a very valuable results like within a seconds or minutes, and expect that learning the tool will take quite long time. The same way as when we are going to school, we start from basics and then we learn calculus and advanced math. So it will not happen that you will just get the software and you will become a professional just repeating the same templates as we provide. You will still maybe miss some details here and there in the setup. And a bit of theory, just briefly I will explain why those limitations appear, where those limitations of 2D FEM come from. So the first thing is that when we are solving electromagnetics in 3D FEM, we are basically solving Maxwell's equations. But 3D FEM is not a tool that can solve those equations in the direct form. In order to make it suitable for 3D FEM, we would need to describe those Maxwell equations into the weak form, into the form that can be solved applying integration operations. So basically, if we would need to describe very simple words how 3D FEM in electromagnetics works, we could say that we have a computational mesh that consists of a lot of elements, and within each element, we are solving integral equation that is basically related to Maxwell equations. And if we are going into specifics, then in TRAFOLO, we are using ElmerFEM. ElmerFEM is open source electromagnetic solver. Sorry, not electromagnetics, it's multi-physics simulation tool. It's very capable. It has been for a very, very long time. And for 3D electromagnetics, it is using so-called AV vector potential formulation. A stands for magnetic vector potential. It has 3 components, X, Y, Z. And V stands for scalar electric potential. Usually we assume that it's in volts, so this is just a simple scalar electrical potential. So we are solving a system of equations that describe integrals that correspond to Maxwell equations, and we do it for a very large sparse matrix, and the result of this sparse matrix is the AV vector potential solution, from which we then can derive the magnetic fluxes, current distributions, and so on and so on. So we are not directly working here with currents or with magnetic fluxes. As you can see in the weak form, in the integral, there are no B or currents. So we are working with potentials, and from those potentials afterwards, the software calculates all the other parameters that are needed. And it's very important to understand that the FEM, the finite element method, and AV formulation in the pure form is not very, very useful, and it will be very limited amount of problems that you will be able to solve with a FEM solver, which you will write yourself. And the reason for that is because we need to put a lot of different numerical methods on top of this pure FEM discretization in order to make it useful for solving magnetic problems. For example, dual-electric bridge, it has litz wire, we need litz wire model. In this case, 3D phase choke with a gaps, we need foil winding model. As well as at higher frequencies, higher harmonics, we would need to use some special models which are called stack models, lamination stack models, to account for magnetic fluxes in the laminations, to account for eddy effect inside. Here, we would need to use circuit models in order to connect those individual turns, and so on and so on. So as you can see, there's a FEM formulation, as it's like in its pure way, we would just be able to solve very simple conducting problems, maybe also some simple core shapes, sorry, not the core shapes, but simple cores, magnetic fluxes in the core, but we will just be able to apply voltage because in a clear formulation, AV formulation, we apply vector potentials and scalar voltages. So all what we could do here is just to apply the voltage from the terminals and calculate the currents and magnetic fluxes resulting from that. But no current excitations, no circuit connections, no litz wire, no foil windings, no. So we can make a conclusion that actually the finite element method is more than a calculator. It's not something that could substitute the calculator, but it's something that can add some value additionally to your calculators that you use, to your Excel spreadsheets. And we are very often asked questions such as, for example, what are the size and frequency limitations for 3D FEM? And as we discussed before, it relies on numerics and physics. It doesn't know about the size of your component. It doesn't care about the size of your component. You can make the smallest component, you can make the largest component. The only, let's say, the only limitation in the context of size and frequency is so-called low frequency assumption. And the low frequency here doesn't mean that we are limited to 50. It just means that the size of your component has to be much smaller than the wavelength that you are solving. So for example, if you consider small component at very high frequency, it will be equivalent to a very large component at lower frequency. But what you will not be able to solve is like a large component at gigahertz frequencies. No, for that you will need to have a wave formulation, like a different formulation, electromagnetic formulation, that will describe electromagnetic field propagation as a wave. So advantages from 3D FEM are many. Very often, if you are struggling with your design, it's overheating and you don't know why it's so, the FEM could be a very great tool to answer those questions. Why my component is overheating, why we have a hotspot, why my winding was burning in some particular area, for example. It can be very accurate. I would say that even likely the most accurate method for most, not for most, but for many applications, it could be the most accurate method. For example, for calculating losses and litz wire. But within those model limits. Also consider that the FEM models are constantly improving, so it means that what we had a year or two ago has or could be like much better than today and will be better in the future. So if you are thinking about the future of FEM, then you don't need to worry that AI will take over your work. If you know how to model with FEM, it's likely that those knowledges will be for a long time, and the numerical methods within FEM will help you to even further improve the accuracy of your model, improve with the speed, and so on. And with a cheaper hardware, 3D FEM, which was like very expensive and very challenging to use, maybe even like 5 or 10 years ago, it's relatively cheap and fast nowadays. So speaking about when should we use FEM, and where are those cases where we have advantage over any other computational methods? One of those could be when you have very non-uniform magnetic flux distribution in the core. We had such cases, we had such designs from our users where the central limb had either larger or smaller cross-section than those outer limbs. And as you may assume, because the same magnetic flux goes through the central and outer limbs, the magnetic flux density can be different either in the center and outside or those outer limbs. So because of that, you have very non-uniform magnetic flux distribution, which changes very significantly with amplitude. And then the question is how you can calculate, for example, losses for such case, or even reluctance for such case, because the magnetic when it's concentrating, then the losses can increase non-linearly. So this is where the FEM has strengths. Another case where we find it very useful is for example, we are very often using Steinmetz equation to calculate eddy losses in the core, and also hysteresis losses, obviously. But in some cases, eddy losses in the core, the eddy loss distribution in the core, in the ferrite, for example, do not match magnetic field distribution in the core. So, for example, here is the magnetic flux, and you can see that the magnetic flux is concentrating at the edges, while eddy currents that are generated in the core, they do not have maximums here at the corners. They have maximums here in the center, where is the winding, so where the eddy currents are generated. So this assumption of the Steinmetz equation about the eddy losses is not complete. So there are different modes for eddy currents within the core. And with 3D FEM, you can account for that. And when it's relevant, especially at very high frequencies, then this could be a very significant accuracy improvement for your calculations. A few other examples where it could be useful. Non-even temperature distribution. So we can account for anisotropic material properties, for example, laminated core. And we can also account for different thermal bridges, gaps, and so on. So the temperature calculations, as they are in TRAFOLO, they're quite relatively easy to calculate temperature, and they're relatively fast. And they're quite accurate if you properly set up the model, if you properly set up the temperatures and heat transfer coefficients. Then the advantage of 3D FEM is to calculate leakage inductance. Usually calculating leakage inductance is rather quick simulation. So here we have a primary and secondary winding. We excite the primary winding while we short the secondary winding. We apply 0 voltage on the secondary winding. And the magnetic flux energy is mostly concentrated between windings. But in this case, because we have a gapped core and so on and so on, so we see that it's not only between windings, there's some portion of magnetic flux here. So you can account for that in 3D FEM. And you can find the reasons why, for example, there is some flux in the core, maybe there is some phase shift or whatever. So this is advantage of 3D FEM, calculating accurately leakage and magnetizing inductances. And last but not least, this is quite obvious, when you're solving solid wires at high frequencies, then you will automatically, if you have enough mesh refinement, if you resolve make your mesh fine enough, you can automatically resolve skin and proximity effect. So if you will have like two windings, you will have proximity effect between. You'll see that, for example, the current between primary and secondary, it tries to concentrate closer to each other, like to on the inner sides. So you will see it automatically. You will need to do any other calculations. But of course, the challenge with that is that you need to have quite good mesh refinement that resolves those effects.